Okay, so today's lesson is going to be graphing exponential functions. And our goal today will be graphing exponential functions using the calculator. We're going to find and determine the differences between growth and decay. That's our objectives for today. We're going to go through that. Again, remember, exponential functions grow through the process of repeated multiplication. And it's important to keep that in mind. So, with exponential growth and decay, we know our formula is going to be f of x is equal to b to the power of x, or occasionally, we can also see it as y is equal to b to the power of x, or let's not also forget f of x is equal to a, that's our initial value, times b to the power of x. Okay, all those are different forms of exponential growth and decay. Exponential growth is a function that is always increasing. That's for its positive. As x increases, y increases also. That's going to look like, the graph is going to look like this. Exponential decay is a function that is always decreasing and negative. It's going to look like this. And as x increases, our y value decreases. Okay? If b is greater than 1, then it's exponential growth. If b is between 0 and 1, then it's exponential decay. So are these growth or decay? Well, f of x is equal to 7 to the power of x. Is this growth or decay? Our base here is 7. Our base is equal to 7. 7 is greater than 1. Therefore, we have growth. F of x is equal to 0.39 to the power of x. Is this growth or decay? Well, we're going to take a look at the base. Identifying our base, it is 0.39. So our base is equal to 0.39. That value is greater than 0, but less than 1. When our base is between 0 and 1, we have exponential decay. So let's go ahead and graph our function. F of x is equal to 2 to the power of x. And to do that, we're going to use our graphing calculator. So we're going to bring that up. Clear any functions you have in it. And you're going to type 2 to the power of x. Now we're given and asked for a table here. And one of the things we can do is we can go directly to the table by going to second graph. We're asked to start at -2, and our value when we plug in -2 is going to be 0.25 or 1 over 4. Our value for -1 is 1/2 or 0.5. When x is equal to 0, our value is 1. When x is equal to 1, our output value is 2. 2 squared is 2. When x is equal to 2, when 1 is our input value, let's go back for that a second. When 1 is our input value, I get 2 to the power of 1, that's going to be 2. When 2 is my input, I get 2 squared, that is equal to 4. Now this value is important. 0, 1 here is for all parent exponential functions. All parent exponential functions will go through the point 0, 1. Now what do I mean by that? I mean that our values for this are something of the form like this, where f of x is b to the power of x, and our a value here would be equal to 1. So all of them are going to go through the point 0, 1, so I'm going to graph that. Another thing is going to occur here as I graph this. I'm going to graph the point 1, 2. I go over 1 and up 2. I go over grab the point 2, I start at the origin, I go to the right 2 and up 4. 1, 2, 3, 4. Okay. And I know this function is going to continue to grow upward like this. However, as we look at this function, my function is going to approach it's going to get smaller and smaller as I head towards negative x. For example, at x equals -1, my value is 1/2. I'm going to put that somewhere between 0 and 1 because that's where 1/2 is. As I go to x equals -2, my value is at 1/4. It's got to be lower than this value and somewhere between 0 and 1, so I put something there. Which each successive value, I am going to come and approach this x-axis but never actually reach it. As I approach this x-axis, as I've said before, I'm going to occur for something that's called an asymptote. A line or a value that I approach but never quite reach. Well, what is that value? That value is y equals 0. My y values will continue to get smaller as I go towards negative infinity, and I'll have an asymptote at y equals 0. I'll continue to get closer and closer and closer to that axis, but never quite reach it. Okay? So now let's answer these three questions. What type of function is it? Well, it's either going to be growth or decay. If we look at the graph, as x approaches, as x gets larger, as we go this way, as x gets larger, y is getting larger. So that would indicate growth. But most importantly, our b value is greater than 1. So therefore, this is growth. Now our domain, which involves x values here. So what kind of inputs would work for this function? Well, as we look at it, any x value works. That means my domain starts from negative infinity and goes to positive infinity. But since I never reach infinity, I put parentheses around it. Now my range here is, I seem to have some kind of floor here. I said I have an asymptote at y equals 0, so I approach y equals 0, but never reach it. If I'm approaching y equals 0, but I never reach it, then I'm going to put my minimum value at 0 and a parentheses around it, because I never quite do reach 0. As we look at our y value, as this function goes through, we see it continually increase. So my value here will be infinity. Let's look at another example. F of x is equal to 1/2 to the power of x. So let's go ahead and type in this function into my calculator. I go to y equals. I'm going to start with parentheses. I like to put those around my base. Alpha y equals. Enter. 1/2. You come off the parentheses here, and we raise it to the power of x. Now we're going to go and graph it. Second graph, we're going to actually bring up the table, so sorry. We're going to go to second graph to bring up our table. And we're going to look at some of these values here. An input of -2 gives me an output of 4. An input of -1 gives me 2. An input of 0 again gives me 1. We've talked about that. This is a parent function of an exponent. Again, a is equal to 1. So we have a function of the form f of x is equal to b to the power of x. When my input is 1, my output is 1/2. And when my input is 2, my output is 1/4. We see that as x is increasing, y is decreasing. We see that my base is 1/2. And that value is 0 is greater than 1/2, which is less than 1. So I also must be decayed. As x increases, y decreases. My base is between 0 and 1. This is a decay function. Let's go ahead and graph this. My value is 0, 1. I'm going to graph. -1, 2. I'm going to go to the left 1 and up 2. -2, 4. I'm going to go to the left 2 and up 4. I know it's a decay function, so I can start drawing it through to the point 0, 1. And it's going to decay at x equals, or the point 1, 1/2. I start at x1. I go to the right 1 and up 1/2. At the point 2, 1/4. I'm going to go to the right 2 and up 1/4. And this value, as x approaches infinity is going to approach y equals 0. So as x approaches infinity, y will tend towards 0, but never reach it. So y equals 0 is an asymptote. Okay. And that's graphing this function. My domain, again, and we'll notice this for all exponentials, is negative infinity to positive infinity. For my range, again, my range is my min to max y value. When I look at it, I look like I have my asymptote at y equals 0. I will get close to 0 but never reach it. Getting close to 0 but never reaching it means my minimum value is 0. It's at the bottom. Because I never reach it, I use parentheses. I see my maximum y value is going to continue to increase as x approaches negative infinity, y approaches infinity. So my maximum y value is infinity. And I use parentheses on that because, again, I can approach infinity but never quite reach it.